Yeah, for like 11 or 12, and I stay up till like.
Because then you have to say, because I have 91 plus HP.
Okay. So let's see what we do with this, right? The first formula tells us the normal components would be the same. So because B is 0 inside the conductor, the normal components is the X components. That means B1X must be equal to 0, right? Okay, so good. And then the second one, you can look at either one, doesn't matter. Let's look at this one. What does that mean? Well, if I'm going to call my air is 1, medium number 1, my conductor is medium number 2, then what is my N2? Going from 2 to 1, so that would be my X hat, right? Are we okay? So N2 is my X hat. And then my JS, the current, is given on the C hat. So let's look at this formula. It say this X hat cross something, my H1 minus H2, must be equal to Z hat, right? So what is the direction of this thing? Must be something in the Y hat. That means I don't need to look at the X components. I don't need to look at the Z components. I only look at the Y components, right? So, okay. So that means my X hat cross H1Y over mu naught. Oh, sorry, that's B. Minus H2Y. H2 is in the conductor. That is 0, right? That is equal to my J, which is 4 over epsilon naught C hat. Right? X hat cross Y hat is Z hat. So what does that mean? H1Y is equal to 4 over mu naught. So what is B1Y? Because I'm asking for B. B is H over mu. So that means B1Y. Oh, did I have it the other way?
I think B is mu.
B is equal to.
No, B is BH. Yeah. I have it the other way. H is B over mu. So this is equal to, this is B1, right? So it's equal to mu naught times H1Y, which is just equal to 4. Right? So my B1, X components is 0, Y components is 4. What about my Z components? Also 0, but why? Why? Same reason. If I have the tangential components is H1C C hat, right? That would be equal to my JS, but JS only has C components. It does not have X or Y. So X hat cross Z hat is what? What is X hat cross Z hat? Say again. Negative Y. X, Y, Z, cyclic permutation. X cross Y is Z, Y cross Z is X. But if you go the other way, that's negative. X cross Z is minus Y. Right? Remember this? Clockwise is cyclic permutation, positive. Counterclockwise is negative. So X hat cross Z hat is negative Y hat, doesn't matter, negative or not. But this side, the Y components is 0. No Y component. So that means this must be 0. Are you with me? So this is your answer. Questions? Yes. Why is X hat and not Y? What? You mean this one? Oh, this is my N. My N hat. Oh, because the normal vector is perpendicular to this surface, right? So it's always either X hat or minus X hat, either pointing to the right or pointing to the left. So, but N2 is always going from medium number 2 to medium number 1. So it depends on how we define which side is 1, which side is 2. Doesn't matter. It's totally up to you. We always take N2. Okay. Any questions? Okay. No questions. Then we're going to do examples on Faraday's law. Sure, this is good, right? This is okay, right? Good. Huh? So we cover all the material we're gonna cover in midterm 2, right? So during the break, you should start studying, reviewing all the homeworks problem, 2 chapters, and all the examples we did in class. And don't try to remember the solutions from the book. They might be wrong, and if I change the problem a little bit, they may not apply, right? So you need to know why did you write what you wrote? All right, so example. In my book, I have a lot of this type of problem. So I'm gonna pick a couple to describe, to do. So I have a loop of wire. So I'm gonna say 3 turns of wires. This is the width, this is the height. And the loop is moving at some direction, let's say to this direction. This is X and this is Y. My magnetic field is X hat 3 plus Y hat X square Y plus C hat sorry, I'm trying to decide what I want to do. What do you do? X is fine. And then it's cosine omega t. Right? The velocity is u is constant. The resistivity, again, I put quote and unquote, of the wire is 3 ohms per meter. Right? What do I want to do? I want to find induced current. Both magnitude and direction. Okay. Question clear? All right. So what do we do? Well, this is a Faraday's law problem. Faraday's law say the induced EMF, the voltage, is equal to minus d flux dt, the flux is b dot dA, right? So that's the same procedure, same steps we're gonna do. So we're gonna find the flux first. It's always defined as b dot dA, right? B is the magnetic field in the space, which is given. What is dot dA? What area am I interested in finding this flux? The flux is how much magnetic field go through a certain area. What area am I interested? The area here in my circuit, right? Right? Are you with me? Try to develop a physical picture. Don't just try to plug in formula, plug in equation, not knowing what you're doing. This is where you would go wrong. So, okay, so fine. So B dot dA. So a few things that I look at. One is the magnetic field constant? Can I take it out of the integral? Yes or no? Is it constant? Is that uniform? No, right? Come on, you can guess. Yes or no? Why not? Because there are whole bunch of x, y, z, and omega t in here, right? It's a whole bunch of function, spatial function, and time function. It's not a constant, right? Okay, so I'm not going to take it out. Dot product, what do I do with the dot product? What does this dot mean? So Faraday's law is a very simple type of problem, and you will see one in the midterm. Whether you nail it or not is really based on your basic math skill, right? Like, do you understand what does that mean? I change something different, then what you do would be totally different. So you need to know why you write each steps. Okay. A dot product, what do you do when you take a dot product? How do you take a dot product? If you have two vectors, A and B, how do you take a dot product? X components times X components, Y times Y, and Z times Z, right? Are you guys following me? Okay. So that means you pick out the components. So let's look at the area. What is the direction of my area? Either in or out, right? It's perpendicular to the screen. That would be either plus or minus C. That means when I do the dot product, I don't have to look at the X components. I don't have to look at the Y components. I only pick out the C components. Are you with me? You need to recognize that, otherwise your problem becomes like so complicated. If you do understand this, then you say, oh, that's easy. That's just my Z components times the Z components of the area. So I only write my B field is really X cosine omega T. That's all I have to worry about in my magnetic field. Right? You need to understand why. Do I do this step all the time? Not necessarily. It depends on how the problem is structured. Right? I might not need to take the dot product if both of them are in the same direction already, like the example we did last time. We don't even have to worry about it. Right? So you need to know when do you have to worry about it, when don't you have to worry about it, and why. Okay. So the next step is the area, dA. What is my dA? Well, dA is my tiny area. What does that mean? It's the area of my tiny typical element. You have to have a structure, have a physical geometry in mind when you write the integral. Don't just say, oh, this is cylindrical coordinate, r d theta, or dr. No, don't. Look at a particular geometry. What's your area? This is why we reveal the definite integral in the first week, right? So in this case, what is my typical elements looks like? What shape? I can do a tiny square. This always works. Or vertical strip, or horizontal strip. No horizontal strip. Why not? Why can't I do this? Because of this. Remember what we say, the integrand must be well-defined, constant, uniform within my typical element. If this is my typical elements, the value x change as I move across this bar. So it's not uniform, constant, well-defined. So you cannot use a horizontal strip, right? You need to know when you can do that, when can't you do that. So the biggest possible typical elements in this case would be my vertical strip, because any point in this strip, I have the same x. X is the value here, the location of my typical element. So I have the same x, it's constant. So what is the area of my vertical strip then? What is my dA? H dW, or this is along the x-axis, I'm going to say dx. So it's equal to times h dx. Right? Again, have a habit of checking your integral equation. The first equation is the most critical equation. If you write it correctly, most likely you will get a lot of points, even if you messed up the math later. If you write the first line wrong, then the rest is a waste of your time, right? Are you with me? So this is the most logical steps. I will check. How do you set up the integral? How do you set up your limit? Does it make sense? Right? Okay. So this is the area. So please double check. Is this an area? Does it has a unit of area, meter square? Right? Don't give me a meter fourth and then call this an area. Right? You need to know that. Okay. And again, you don't just add dx there because you think you're going to do an integral and you need to have a dx. You don't. This is the area of the typical element, has a reasons to be there because of this. All right, so now x dx, that's easy. What's the limit of my integral though? What's the limit of my integral? You say, well, from here to here, so is that from 0 to w? Yes? Yes? Okay, unfortunately, no. Okay. Why not? Well, because when I draw this, maybe at time 0, at this corner is located at the origin. But you're not writing a very specific time. You should write it in general. The loop is sliding to the right over time, right? So at some times later, you can imagine the loop is like right here, moving to the right. So this corner is no longer 0. You say, well, why? What does it matter? I'm still integrating across here, the same width, right? So I will have the same area. Yes, the area will be the same, but the magnetic field going through this square or rectangle will not be the same magnetic field going through here, even though the area is the same. Why are they not the same? Because I have an X in the magnetic field. The more I move the coil to the right, the stronger the magnetic field is. So it does matter. Yes.
So the
You're right, because the B field change, right? Does it always change? No, depends on what I wrote here. Depends on what is given here. If I give you a constant, then you don't have to worry about it. Right? Okay. That's why if you look at my book, I have like 5 or 6 problems given basically the same thing. The rectangular moving and then a B field. But then my B field always change the different function and form, and the movement sometimes is going up, sometimes it's going to the right. And so any little things change, your solution will be different. And I keep changing little things and put in the exam, and that's why you get another problem, and then change little things and put in the exam. Students still did not figure it out, Why? Because a lot of students just remember solutions. You don't understand the solution. Right? If I change the velocity, the loop is moving up, then the solution will be different. Right? Or if I don't put x here, but put y here, then the solution will be different. So you need to understand why we do things that we do. Right? If you have time, I encourage you to go through all those problems in adult. If you do, then you really understand it. Then it doesn't matter how I change it, you know what to do, right? All right, so what do I do? I'm gonna call it at time is equal to 0, the corner, thank you. The corner of my coordinate, I'm gonna name it something, maybe x naught or something, right? So that means distance is x naught. Then on the other corner, that would be x naught plus w, correct? X naught is the location of my corner. So it's x naught to x naught plus w. Right. Do I always have to do that? No, that's because I'm moving the loop to the right. If I'm moving up along the y-axis, like moving up vertically, then I don't have to do it on the x. I have to do it on the y, but I don't need to do it on the x. Right? Yes.
If the field was like not, if it, like the loop was not moving, it was static, it would have been 0 to w to work 300.
Yes. All right, so here we go. So now when I do this integral, this is why you have to write d something. Don't give me just what is cosine omega t and that what is that equal to. That is wrong because what is that integrating on? What is the variable? If it's dt, then you have that becomes a sine. But if dx, then it's still a cosine, right? So don't skip that. If you have an integral sign, make sure you have a d something. What are you integrating on? Okay. So here I have a function of time here, but then I'm integrating on dx. So I'm really integrating on x, not omega t. So this term, cosine omega t, becomes a constant in this integral because it's not a time integral, right? So try to be, try to keep track of everything nice and neat when you're doing math. So here, if I would do one more step, I would say h is a constant, cosine omega t is a constant. So what I really have is x dx from x naught to x naught plus w. And then to do this integral is just equal to h cosine omega t. And then this is x squared over 2. You vary at this, so it's x naught plus w squared minus x naught squared divided by 2, right? And if I expand that, the x naught squared would cancel, so that would end up getting h cosine omega t divided by 2. And then I have 2w x naught plus w squared, right? The x naught squared cancel. I tried to write the omega better so it would not look like a w, but sorry about that. Omega w. So far, so good. So I'm a little bit picky. I'm going to, you see, I like algebra. So I see a w here, w squared, I'm going to factor one out. You don't have to do that, but it's just me. Because then, I'm going to do the t, absorb the 2 divided by 2 in that 2. Why not? It's up to you how you do your algebra. I don't care. divided by 2, so this is x naught, this is plus W over 2, right? Nice and neat. Okay. Now, what's the next step? This is the flux. All this is calculating the flux that goes through this rectangle at any given time. And to find the EMF, I need to take a derivative because, so the EMF for number of turns would be minus n is number of turns, d flux dt. So it's a time derivative of what we have and multiply by number of turns, which is, I'm just going to call it n. I don't care what that is. So what is the time derivative of this? So what is the time derivative of this? Well, we have two functions of time. Cosine omega t, of course, is a function of time. X naught is also a function of time, right? Because as the loop moving to the right, this is the location of x naught. And if this velocity is constant, you can write x naught is equal to u times t, for example, right? It's a function of time. But let's just say it's a function of time. So let me take a derivative first. So this are two functions of time. So we have to apply product rules, right? What is product rule? You take the derivative of one, holding the other function constant, and then plus the derivative of the second one, holding the first function constant, right? So I'm gonna take a derivative of it, and HW is just a constant. I'm gonna take a derivative of the first one first, and that would be negative omega sine omega t, right? And then the second function, I'm just gonna copy it. Correct? Plus, I'm going to put everything outside. Plus, the second function, the first function, cosine omega t, times the derivative of this function. So that's just dx naught dt. Right? But what is dx naught dt? That's just the velocity along the x direction. There's nothing more than u. So I'm going to rewrite this. I'm going to rewrite everything here. The EMF is equal to negative of n d flux dt. I'm going to absorb the negative here. So n times hw. And then I'm going to say omega sine omega t, x naught plus w2 minus cosine omega t times u. We okay? That is the EMF. That's the voltage. So to find the current, induced current, of course, is this EMF divided by the resistance. So I'm not going to rewrite this. This is just my voltage, EMF. What is my resistance? Let's go back to the problem. The resistivity is 3 ohms per meter. So how do I find the resistance of these 3 loops of wire? How do I find the resistance? It's just 3 times the total length. The total length is 2W plus 2H times number of turns, right? Right? So let me write it down. So the resistance is 3 ohms per, this is the ohms per meter, times 2 H plus W times the number of turns, right? Which is 3 turns, but this n always cancel. So I always just leave it out. And you simplify it, of course, right? And that would be your answer, except the direction. We need to figure out the direction. So I'm going to pause a little bit, give you time to write things down so you'll be paying attention to me when I'm going to talk about the direction. All right. If you look at the problems in my book, we have things can change, multiple things can change at the same time, right? Not just one at a time. So in this case, 2 things are changing. What are they? Well, one is the magnetic field going into the space is oscillating over time. So that's changing magnetic field. So the magnetic flux change, so that would induce a current. The second thing is you're moving the loop in the magnetic field. Even if the magnetic field is not oscillating, by moving it, because the magnetic field is not uniform in space, you also induce a current, right? So 2 things will induce a current. Do they induce a current in the same direction? If so, that's good. Then you just need to find out one direction and then you know both, right? But what if they are not? What if they are conflicting directions? Then how do I decide which direction will dominate in this current, at least when time close to 0, when time is small, right? Why do I always focus when time goes to 0? Because if the equation, the formula works when t goes to 0, then the sine and cosine will take care of the flipping, the AC oscillating current. So all you have to match is one particular time, t is 0. Okay. So how do I know they are in same direction or they are conflicting direction? You look at your expressions, your current, which is basically your EMF, right? You look at these functions here. You always have something either sine omega t or cosine omega t. If you get both of them a sine, like sine omega t and then sine omega t, then that means they oscillate at the same time. That means they're always in phase. That means they're always in the same direction, right? Or they both are cosine. Then you don't have to worry about which direction dominate, because you just need to find one. If one of them is sine, one of them is cosine, this is when you have to decide, okay, what do I do? Which direction is dominant? Okay. Are you with me? So you look at this, you can tell, are they conflicting? If they are, then which one dominate, right? And then you need to figure it out. So sine and cosine, we say all you have to do is fix a particular time. What time? When t goes to 0. So when t goes to 0, what is sine omega? What is sine 0? 0. That means when time is small, this term is not contributing. All the direction is contributing from this term. Are you with me? Okay. So I'm going to say from Lenz's law, I'm going to write this. So when t goes to 0, the cosine omega t, the cosine term dominate, right? But where does this term come from? This term comes from taking the derivative, the change of this, the change of the location of the corner. What does that mean? The moving of the loop dominate this direction, not the oscillating magnetic field. The oscillating magnetic field give me this term. This term comes from moving of the loop. So you say when t goes to 0, moving of the loop dominate. Right? Are you following me? Okay. Then you go to your picture here. Your original picture. And look at our picture here. When t is 0, right, goes to 0. What is the direction of the magnetic field through this loop? The C components only. What is the direction? Is that pointing out or is that going in? It's pointing out because it's plus Z, right? Don't get this part wrong because this is like, you don't have to do calculation, you can have the credit of the problem. So don't get this part wrong. So again, when t is 0, right, this is in the plus C direction. So that means, where's my Z? This is X, this is Y. Y, where's my C direction? In or out? Out, right? There's no if, no but. It's always out, right-hand rule. So that means my Z is pointing out, my magnetic field is pointing out when t is 0, right? Okay. So that's the first question. I'm going to write this down. So when you go back and look at it, you remember. I'm just going to write here. Let me write again. When t goes to 0, the moving loop dominates. And the B field is out of the page. Is this B field increasing or decreasing? So how do I know? Look at the function again. Is this magnetic field when t is 0? Is that increasing or decreasing? Decreasing because cosine is a decreasing function. When t is 0, it's maximum 1. Anything above 0, right, it starts decreasing. So I'm going to do this again. I'm going to say my magnetic field is out of the page, but decreasing. So according to Lenz's law, the system, this loop is going to induce a magnetic field. So what is the direction of the induced magnetic field? If the B field is coming out but decreasing, what is the direction of the induced magnetic field has to be? Again, what does Lenz's law say? He said, I want to keep the magnetic flux constant. If I get 10 units of magnetic field coming out when t is 0, now I'm getting less. I'm getting 9 and 8 and 7. So what is the induced magnetic field wants to do? Make up the difference, right? So what's the direction of the induced magnetic field? Has to be out of the page. Right? Are you all with me? Don't get this part wrong. This part is the easy part. Okay. You want to keep the magnetic flux constant, magnetic field constant. So your question? Decreasing, I didn't say. I say decrease.
Yeah, the field.
The field is decreasing because cosine is decreasing function.
But isn't the X and that's
Okay. So you say, why is that decreasing? Because X is increasing, so it's increasing, right? So we say no, because we only look at, oh, sorry. We look at the moving. You're right. So let me do it again. The B field is coming out but decreasing. I actually don't need to know the decreasing. It's coming out. But the moving loop dominate, right? So as the loop move, would the B field, would the flux increase or decrease? Thank you. So we start from here. Assuming the B field does not change. Now I move the loop to here. Will I get more flux or less flux?
more.
X
Which
in
one
here,
goes faster? What is
huh?
sine effect, basically? For small. Yeah.
Do I get more flux or less flux? More. Because I have an X here. As I move more to the right, the magnetic field strength increase. Okay, so it's actually increasing. Yes, cosine make it small, but I'm not looking at the oscillation part. I'm looking at the moving loop part because moving loop dominate, right? So the moving loop would make the magnetic flux increase. The oscillation part would make the flux decrease, and they're conflicting. And so we say, well, how do I know which one dominates? I look at T0. At T is equal to 0, the moving loop dominates. So I only look at the flux, the magnetic field is not changing, just moving the loop. What direction of the induced current? So the B field was still coming out, but increasing. So that means the induced magnetic field must be into the page to cancel it. So if the induced magnetic field is into the page, that's my thumb. My induced current would be clockwise. Right? So depends on how you want to write your answer. If my answer here, if I say I'm just going to keep the whatever the sign I have here, then my cosine term is negative. So I'm going to say negative, meaning clockwise. By clockwise really mean negative. That means in my answer, in my expression, I induce is equal to blah, blah, blah. When that expression is negative, my current is clockwise. When that expression is positive, that becomes counterclockwise. Yeah. Which part of what? In the equation or in the oh. So look at this expression again. If you have a cosine and a sine term, the cosine term always dominate. But where does this cosine term come from? The change of what? Change of the corner, change of the location. So it's the moving of the loop. This one, the sine term is come from the taking the derivative of the cosine. That's the taking the derivative of the B field. So this is from changing the B field oscillator. This is from moving the loop. Okay. All right, so let's go over this one more time. Doing the math, because there are two things changing, we say we take the product rule. The product rule tell us to hold one function constant and only look at the time derivative of the other function. So that means I assume one function does not change, and then I look at the effect of changing the second function. And then plus, now I hold the first function constant and take a derivative of second function. This is exactly what we do with the Lenz's law. The Lenz's law say, okay, if I want to look at the moving loop, what's the induced direction due to the moving loop only? I'm holding the B, not fluctuating, not oscillating. I only look at the effect of what happened when the loop moves, but the field is not oscillating, right? And the other case would be, well, if the loop doesn't move, stationary, but the B field oscillate, what would the direction be, right? In that case, it would be opposite. Any questions? We can do one more, yeah.
For the direction, do you have to specify? Can you just say at time equals 0 is clockwise, or do you have to say when it's negative, it's clockwise?
I want you to tell me this because because if you just say clockwise or just say negative, it can be confusing. Let me give you an example. Let's say if I have an object coming down gravitational force. So is this force minus mg or is this force mg? Are they the same? Are you telling me the same information or how should I interpret your answer? You know what I'm saying? So, I mean, the more correct way is you tell me which way you define positive. Let's say if this is my y-axis, then I say this is minus y hat, then that would tell me going up is positive, coming down is negative, for example. But then you can also define y coming down. And then this would be okay. So you need to tell me what is positive and what does your answer mean, right? That would be a better answer, a clear answer. If you don't specify all this, then it's up to my interpretation when I read your paper. I say, does he know what he's talking about? Or he's just like, I don't know if I should give him all the credit, and so you don't want that, right? Okay. Any questions? Let's do one more problem, and then we move on. We don't have time to move on. Oh my God. Should I just skip the example and do you feel like you know what to do now, or do you want to see more examples? How about oscillating one? So I have a loop with radius r, but r is actually oscillating. It's equal to 2. 2 minus sine or cosine doesn't matter, sine omega t. And then I also put this in the presence of magnetic field. The magnetic field is, again, this is my x, this is my y. So the magnetic field is 2x hat minus 3 y hat plus four c sine 30t. One loop. So again, I'm looking for induced current. Yeah, this is good. Okay. So what do we do? Again, Faraday's law, right? I mean, the first thing you have to recognize, if this is a Faraday induced current, it's always a Faraday's law problem. And Faraday's law problem, you always want to find the flux, and then you take the time derivative. It's always the same step. So the flux is defined as B dot dA. Okay, B is given. Great. What is dA? I need to do integral. So what do I do? Dot product. First of all, dot product. What is that? What do I do with the dot product? Same thing we did this last time. What did you do? What did we do? What's the direction of dA? Has to be in and out, has to be in the C direction, right? So that means my dot product, I only pick out the C direction, C, right? Of the B field. These two components of the B field does not do anything to our problem. So we can ignore it, right? So that means this is 4 cosine 30t. That's my B field. That area, what area am I looking at? What is dA? What's my typical elements? What do I do? What is my typical element? What do I write?
A disk.
Come on, try it, huh?
A disk.
You did what?
A disk.
Do you need to do integral at all? Why not? There's no penalty for wrong answer. Come on. I don't know you. I don't know your name. Why not? Yes. Constant because there's no X and Y in here, right? You say, wait a minute, but there's a T in there. Doesn't it make it non-constant? They no, why not? Because this is a spatial integral, the area, right? This is a dx, dy, dz type of integral, not dt. So the time is a constant in this integral. So the whole thing is constant. I do not need to do integral. It's really b dot a. So this is just b times the area of what? Of the whole circle. Right? Okay. So now from here, it really depends on how you like to do your algebra. I see a lot of people would like, oh, I know what R is, and I'm going to expand this, and I know how to do R square, and have a. You can do that, but that's just you create more terms, take longer to do your math. So try to remember what you would have done when you're taking a math class. So I'm just going to write this. I mean, this is it, right? I'm not going to do any more. So what is EMF? Induced voltage, negative d flux dt. So it's a negative of time derivative. Now I have a t here, but then R is also a function of time, right? Because it's a function of time here. Two function of time, product rules, don't forget. So, but it's funny because so when we're doing all these product rules and in the exam, only one thing's changed, and people will still force to do the product rules in your answer because that's what you've been doing in class. So I'll see what happened this time. Anyway, so I'm going to take the derivative of first function. All the constant is 4 pi. I'm not doing the R square, so negative times 30 sine 30t, that's my first term. And then plus, I'm just going to keep like everything. 4 cosine 30t, I have the pi, and then the derivative of R squared is 2R dR dt, right? So it's 2R times, what is dR dt? I come up and look at it. dR dt is omega cosine omega t, right? With a negative. Right? Then you only have to do one integral, one derivative. So simplify a little bit. I have a 4 pi. I have a negative. Oh, the negative we cancel with this negative. So actually negative of everything. Right? Because of this negative here. So 4 pi. I'm going to take one out. So I end up getting 30 out. Sine 30t plus 4 4 pi is gone, R is gone, so I have 2 omega cosine 30t cosine omega t. Right? And you simplify it the way you want. And then to find the so to find the current, of course, it's V over R, but foolishly, I use the capital R for radius, so I cannot use R for resistance. So I'm just going to say divided by the resistance. Right? We didn't really specify, but anyway, so it's basically this, divided by R. Any question? The math is not too bad, right? Just taking the product rule and try to, you don't have to expand R, right? So don't think you have to substitute what R is given. Okay, so you don't have to make it a mess. It's not wrong, it's just make it harder to keep track of, right? If it looks simpler, then we tend not to make mistakes. But anyway, looking at this, I have a sine term, I have a cosine term, right? Okay, so it's time to do the direction. So I'm going to say, when t is equal to 0, which term dominate? Tell me. Is this term dominate, right? But where does this term come from? It's taking the derivative of what? Of the field or of the radius? Of the radius, right? Because this is 2r dr dt. So you say when time is 0, the radial oscillations dominate. Right? Right? Are we okay? And then look at this picture. We say the radius oscillation dominate. So at t is equal to 0, what's the direction of the magnetic field? Out, right? Come on, guys. Participate. Out, right? So the magnetic field is out. Okay. And the radius is that expanding or contracting when t is 0? Expanding or contracting? So sine function, is that increasing function or decreasing function? Increasing function. But you have 2 minus the sine, so the radius, is that increasing or decreasing? Decreasing, right? So I'm going to write that down first. R is getting smaller. B field is coming down, it's coming out. R is getting smaller. R is decreasing. So that means the flux inside the circle is getting smaller, right? Because the circle is getting smaller. So the induced magnetic field must be in what direction? Out, right? To make up the difference. I have a lot of field coming out. I'm getting less. So the induced must be coming out to make up the difference. So if this is the direction of the induced field, then my induced current must be clockwise or counterclockwise? Right, so you say going this way, and this is a positive number, so good. Positive is counterclockwise. Right? Again, The magnetic field problems could be harder because you have a lot of curls, a lot of cross product, induced currents, boundary conditions. Faraday's law problems are really easy. You just have to make sure you understand the dot product and your Lenz's law, right? And remember how to do the product rules. That's not too bad, right? So study it, make sure you nail this problem. If you only nail one problem, you already are doing well in the exam, right? Okay. Any questions? I'm not going to let you go. I'm going to make use of my time. Come on. So I want to start on the next module because I realize we really don't have a whole lot of time. So the next module is, we'll go back. Yeah. Is what I call the Maxwell equation, which leads to the wave thing. So the Maxwell equation is very short. We already did the boundary condition. So I just want to say a few things on this. 5 minutes. So remember, we have this 4 equation we call the dynamic equations, right? Gauss law, Faraday's law, no magnetic charge, Ampere's law. And so when Maxwell looked at this 4 equations at a time, he realized this 4 equations are not consistent. What do we mean by that? So if I take the curl of so we have this one from Faraday's law. This is basically Faraday's law in a differential form. If I take a divergence on both sides, like I can take a divergence here, divergence here. Divergence of the curl is always 0. Divergence of the curl of any vector is 0. You learned that in calculus. Come see me if you want to know more. So that means that, but divergence B is also 0. This is the third equation. We say there's no magnetic charge. So 0 is equal to 0. Everybody is happy. Now we do that to the other equations, the Ampere's law. I'm going to take a divergence on both sides. Divergence of this is 0 because divergence of the curl of any vector is 0. But divergence of a current density, why is it 0? Right? There's no physical evidence to this. So Maxwell say that's not really correct. So I'm going to skip all this. At that time, remember, they have very limited physics knowledge. And the closest things they know is the aerodynamic of the fluid dynamic. They study making wine. So there's something called continuity equations, like how much wine flows through here, and if the tube is thicker or narrower, then it will move faster. That type of equations, the equations. So he's just going to use that and say, okay, if I put that density, right, define it as, in our case, we know it's a current density, then everything is fine. So what I want to teach you is this. I'm not proving anything. I'm just saying when Maxwell look at Faraday's, right, we first have curl of E is 0. Again, this comes to the Kirchhoff rule. If you go the voltage go around closed loop is equal to 0, that means curl of E is 0, 0. But then Faraday say, no, if the field change over time, this is not 0. You have to add a minus dB dt in it, a change of flux. So Maxwell say, I'm going to play the same game to the Ampere's law. You say curl of B is equal to this. You say, no. If the electric field change over time, you need to add a dE dt term, just like I add the dB dt terms in here. If I do that, then I take the divergence, everything is fine, right? So in the book, this is called the displacement current because this is basically dB dt, displacement current, right? What does that mean? That means that means it's not a wheel current. That means there's no free charge going from one location to another. But it's the polarization oscillating over time that appears the charge is oscillating, is moving, but it's not really moving. Okay. You know what I mean, right? When you say moving and not moving, right? So remember you see some of the picture. If you go through one of the wheels with like you only see part of the picture. If you move at the right frequency, the right speed, you can see the picture is moving, right? That's what I mean. So combining, adding this term, Maxwell take credits for all four equations. That's why he's a smart man. He only add one term to this four equation. He claimed the ownership of all these four equations called Maxwell equations. Now combined with this four equation, it describes everything, including electricity, magnetism, and optics, right? That's why this Maxwell equation is so famous, because it's a grand unification, electricity, magnetism, and optics. In the past, they are thought to be a different thing, but now it's really one of the very same. So I run out of time. We'll continue. That's the exciting part, starting now.
Are you telling that? Ampere form? Hold on. You telling me that? Like, what do you mention the line?
No, it's studying fluid. Yeah, not just, but at that time, people studied fluid because of wine industry was the driving. It's a high-tech industry back then. Pretty much, we have to drink enough to